thank you all for this opportunity. My name is Jacob, and I'm here to present work that I'm doing for part of my PhD with Sophia Franco here as well. And what I'm going to present to you today is tree canopies, urban green amenities, and the residential real estate market. And we're using remote sensing and spatial bionic applications to Lisbon, Portugal. So just to briefly go over today's presentation, I'll start with the motivation and the research question, go briefly through some literature, then I'll spend some time on the data and the sources and how we collected our data. I'll go through the empirical specifications and the spatial diagnostics that we ran, and then I'll present the results from the spatial and the OLS model and some wrap-up policy discussions and conclusions that we're getting. So just to motivate this, we wanted to look at what impacts do urban green amenities have on the residential real estate market. And we wanted to focus specifically on urban green amenities and not other types of green amenities that are commonly used, such as agricultural land at the urban peripheral. And we wanted to look at how can we capture the heterogeneity of these urban green amenities. So we don't want to look at just one generic type of open space, but we wanted to disaggregate this by different types of open spaces, the types of trees and different tree canopies. So one of the big contributions of this paper is that we're going to look at trees and specific types of trees, and again, overall measures of greenness in an urban area. And then further, using some interaction text, we wanted to look at do green amenities, in a sense, attenuate urban risks, specifically on flooding, or can they accentuate urban aesthetics? So just to give you kind of an outline of some policy relevance to Lisbon specifically. So in Lisbon, there's a big debate going on about one of the main thoroughfares, it's called the Segunda Circular, and one of the big issues of debate is whether they should be planting trees or shrubs in this area, and further, what is the value of these trees? So they're estimating that around 10 million euros is going to be spent to allocate to planting trees along this urban thoroughfare. But we want to look at, what is the value of trees, and are they planting the right types of trees, for example, and whether the costs outweigh the benefits. Further, there's a big petition going on to turn an abandoned lot into a large open central park type area. So there is a preference that people do want green spaces in an urban area. And lastly, the municipal government, the Câmara Municipal de Lisboa, has used green planning as one of their cornerstones of their urban planning. So they want to link the city through different green corridors, and they want to increase urban biodiversity with different types of trees and animals as well. So there's been a lot of literature on open space. Most have looked at, proximity to general types of open space, but some, such as Anderson West, do look at different heterogeneity aspects in terms of how different neighborhoods interact with open space. They find denser neighborhoods tend to be valuing parks more, so those in the central business district. There's some along the lines of what we want to do is Chombrowski and Cronenberg. They look at a really fine disaggregation of open spaces. I think they have 9 different classifications of open space, and this is along the lines of what we would like to do. In terms of tree canopies, getting the data for tree canopies and trees in a city is very difficult, so there's a lot less studies on this. However, Donovan and Buckley in the US looked at in situ sampling of trees, and this is obviously very time consuming, but they do find the tree canopy and the size of the tree canopy is the most important. And then Sander and all also use some remotely sensed tree canopies to find that there's a positive influence on housing prices. Our data sources, Câmara Municipal de Lisboa provides the public database of all the green spaces in the city, all the location of the trees. So we have a database of about 52,000 trees located throughout the city. In terms of the location of local amenities, this comes from a city service development kit from the Lisbon City API. This provides the location of hospitals, so we use all this for controlling for distance to hospitals, to schools, for the central business district. Our housing price comes from Confidencial Imobiliaria, and we have asking price and structural characteristics. And the remote sensing part of this study uses aerial photography with a 50 centimeter resolution of Lisbon, so I'm going to talk about that briefly in a bit. And then we use census data to control for neighborhood characteristics. So what do we mean by urban green amenities? So I've broken this down into 2 parts. We first look at green spaces or different types of green spaces and urban street trees. So in terms of the types of green spaces, we focus on parks and gardens. So we classify these by different sizes. Then we also look at urban forests, which are more dense and tend to have more recreation aspects for the residents. We look at cemeteries as well. Monsanto is the largest urban forest in Lisbon. It covers about 10% of the total area of the city. We did look at the Tagus riverfront, so the Tagus is the main river going through Lisbon. And then further, we looked at playgrounds as well. In terms of urban street trees, we are able to classify the trees mainly based on how the foliage is. So we can look at palm trees, shrubs, for example. We can look at trees that stay green throughout the year and trees that lose their leaves in the wintertime. And we assume that this is going to have an impact on the residential real estate market, mainly through effects such as shading and blocking of view. So here are some examples of two parks in Lisbon, just to give you an idea of what we're talking about. The first, Jardim da Stella, is a much larger park, where the second, Jardim da Prada, is a very small neighborhood park. So we wanted to classify this by size so that we can capture different effects. Monsanto, of course, you can see is very dense and green, those are trees there, right in the middle of the city. Quintas Contas is another urban forest in the city. There's a lot of recreational facilities there for residents. Cemeteries, although they are a type of open space, tend to be, the social context of cemeteries very different than for a park, for example. And we did look at the Tagus riverfront as well, but we do not include it in our final specifications due to some multiplicity concerns. Just to give you an idea of where these are located, you see this is Lisbon here. Down along the south here is where the Tagus River is, and you can see that the dark green is where our urban forests are, and the playgrounds and parks and gardens are located more or less spread out throughout the city. And you can see we have cemeteries down at the bottom, and some up around the north end of the city as well. Highlighting the different types of trees that we have. So we have broadleaf and conifer trees. Now these are both evergreens, so these are trees that keep their leaves throughout the entire year. We also have deciduous trees, and these are the most popularly planted in Lisbon, and they're the trees that lose their leaves in the wintertime. Palm trees we also include. They're a bit more aesthetic and more in the historic and cultural areas of the city. Bushes and shrubs are more low-lying trees, while we also have monumental trees. Monumental trees are more living history types of trees. Now in terms of this, again, Lisbon, I wanted to point out where we have areas of historic protected zones, which are represented in black there, and in white we have areas where there's high flood risk zones, because we use these as interaction effects with our urban green measures. Here we have the location of the different palm trees, monument trees, and the shrubs. You can see they're pretty well spatially spread out throughout the city. These are our evergreen trees, again throughout the city, mainly planted along the main the streets, and then the largest, about 26,000 deciduous trees located throughout the city as well. Now what we wanted to do to complement this is to look at remote sensing of tree canopies. So it's very difficult to get tree canopy or environmental data to use in spatial hedonic regressions. So we're using aerial photography or satellite imagery to capture the tree canopies in the urban area. So this has been done a lot in more forested areas, but in urban areas it's very difficult to disaggregate trees versus types of roads, for example. So we use 50 centimeter resolution aerial photography, and this classifies the ground cover. And it's a one-class support vector machine learning algorithm, and it's able to identify trees throughout the roads and the buildings and the grass. So it identifies trees, but not grass. And then it just uses the pixels to classify this based on the algorithm we supplied. We find that approximately 8% of Lisbon is covered by tree canopy specifically. So here is the classification of Lisbon specifically. You can see two zoomed in areas, but I'm just going to show you that here's a very zoomed in area of Lisbon. So what I've done is to highlight all the tree canopies that the classification algorithm gives us in black. We have about a 90% accuracy rating, so the algorithm we use is able to capture about trees 90% of the time, so it's fairly accurate. And we, again, were able to aggregate this up to look at the percentage of tree canopies in different neighborhoods to control for that as well. So our empirical strategy, we know there's going to be spatial dependence in the real estate market, so we test and we look for this. We do a spatial hedonic decomposition of dwelling price by the attributes. Based on the AIC, the Moran I, the LM test, and the variable significance, we go with the spatial error specification. So here's our specification controlling for the spatial component in the error term. We control for structural characteristics, neighborhood characteristics with the census data. We have accessibility and spatial characteristics like proximity to our green amenities and the tree canopy coverage, which are the two variables of interest in this study. So we did test 4 different spatial weight matrices, and the matrix that we were, the results that we were most comfortable with went with the inverse distance squared for all properties within 500 meters. And just to present the spatial diagnostics, but I'm just going to highlight the second spatial weight matrix. So we have 3 different models. The first looks at the disaggregation of trees by type, and then a model each for interaction effects with protected zones and flood risk. So all the diagnostics point that we should be controlling for spatial dependence in the data, and we go ahead with the spatial error specification. So multicollinearity is a big problem when we're looking at these problems, especially when we're looking at accessibility data. So in models, when we're controlling for distance to certain types of amenities, if we do find that we have a high VIF, then we do control for the proximity to the amenity using concentric buffer rings instead, and that manages multicollinearity quite nicely. So we had no significance in introducing an aggregate measure of trees, so that's why we declassify it based on tree type. And then we look at 2 models of interactions, looking at flooding and protected zones. So some neighborhood geography variables, so you can see that protected zones have a positive impact on the housing price. So here I'm presenting the 3 models with the OLS and the spatial error models side by side. In terms of monuments, so these are historic monuments. Lisbon's a very historic city. So we look at the number of monuments in 100 meters, and we find this is positively related as well. High flooding risk, we don't find any significant effects here, but it is consistently negative throughout the different specifications. And then we also control for view of the river, which is very highly significant for the asking price of dwellings. So in terms of our green amenities, I'm going to first focus on Monsanto. So Monsanto, like I said, is the largest urban forest in the city. We don't find any significant effects at distances less than 750 meters. So Monsanto, we controlled for by looking at concentric buffer rings around the forest. But we do find significant positive effects coming from 750 to 1,000 meters away from Monsanto, and this is about driving distance to this urban area. So the reasons why we might not have significance at closer levels at Monsanto, it's quite a busy area. There's a lot of thoroughfares going through the forest, so it may be due to the undesirable properties of living next to high traffic areas. In terms of distance to cemeteries and playgrounds, we find that there's actually a negative effect on property value. So here there's a positive coefficient sign, so that means as you're increasing distance, you're moving away, the prices are increasing. So prices are going to be decreasing as we move closer to this amenity. So cemeteries and playgrounds tend to have negative effect on property values. In terms of the parks and gardens, so we looked at 3 disaggregations of parks and gardens, which are small, medium, and large. We see that there's a positive effect of being closer to small and medium parks. However, at a larger park, when we move closer to them, there's actually a negative effect. And this negative effect is kind of tapers out a bit when we look at the spatial specifications. We lose some significance there. So what may be happening here is that parks and large urban parks and urban forests tend to be about the same size. However, it may be that the recreational facilities associated to the urban forest are more attractive than the urban park. So if someone's going to decide to go to one or the other, they may decide, or they may have a preference of moving and going to the urban forest where there's recreational facilities. In terms of our trees, so we looked at monument trees, shrubs, palm trees, deciduous trees, evergreens, and the percentage of tree canopies, which we captured with the remote sensing. So in terms of monument trees and shrubs, so these are more aesthetic trees. Monument trees, no significance, but one significance there, but consistently positive. So this is the number of trees in the census tract neighborhood. Shrubs tend to have no significance, but a consistent negative sign there. Palm trees, we found that actually have a negative impact on housing prices. So you would expect palm trees to be more aesthetic and more complementary to housing prices, but it may be because palm trees can be planted along roads and in more populated, culturally significant areas. Deciduous trees have a positive, strong effect on housing prices. So more deciduous trees tend to increase prices, and these are the most common trees located throughout the city. There's about 26,000. However, when we look at evergreens and tree canopies, there's a negative trees that stay green all year round and higher amounts of tree canopy in a neighborhood tend to have a negative impact on property prices. And what's suggested in some of the literature is that these types of evergreen strands and high canopy trees may actually be kind of inhibiting views from properties and might actually have a negative effect from shading in the summertime when kind of sunlight is valued. This shading effect might actually be driving a negative effect on property prices. Now we look at the interaction effects. So we did two models, one with a protected zone interaction and one with a flood risk zone interaction. So if we focus first on the protected zone, we see that the sign of the coefficient on the evergreen interaction effect is still negative. And this kind of goes along with the idea that this shading or view obstruction from the evergreen trees is negatively impacted, especially when we look at protected zones. However, palm trees interaction, so palm trees in protected zones, have a positive impact on housing prices. So we said palm trees are more aesthetic, and so this may be driving this result. In terms of evergreens, palm trees, and tree canopies, however, we see that there's a positive ecological spillover effect. So when we look at flood risk, there's a positive amenity value for these three types of trees, even though there's a negative overall standard effect from these amenities. So just to wrap up some discussions, we do find that view has a positive impact, so view of Patagas. So these proximity to different types of parks, small and medium neighborhood parks tend to be more valued than larger parks. Large parks, the amenity value of these may be captured by urban forests. And Monsanto does have a significant influence at a certain distance. And then again, cemeteries, not desirable for residents to be so close. To trees that have their leaves all year round tend to have a negative impact. This is potentially due to shading. However, we do find some ecological benefits to these types of trees in flood risk areas. Palm trees are complementary with historic zones, while evergreen trees which obstruct views may not be. And planners, when they're considering planting different types of trees in different areas, they should be focusing on the highest positive spillover effect to the residents. And overall, it seems that view and blocking of view and sunlight may negatively affect prices. So we did find that different types of green amenities have different varying influences. Considering a global proximity to open space may be misleading. Spatial models do tend to have an improvement over OLS, so we should be controlling for spatial autocorrelation here. And new avenues are open when we're able to look at different types of ways of capturing variables such as remote sensing to get these canopy variables. So that's it. So thank you very much.
Last Sunday I had a discussion about my view on trees and gardens and how it is valued by other than the residents of the garden. So I had few questions, but as I was reading, I found my answers. So I stick to these two. And you say that you use data for 2-bedroom flats.
Yeah.
And I was thinking if people like families with children, aren't they more likely to buy bigger flats, and aren't they going to value more green spaces and playing grounds when for such context? And I was about to ask, why don't you control for metro stations? Then I saw in the appendix that you control for metro stations. But I was thinking, couldn't you, instead of measuring distance, measure time to the central business district? So these were my 2 points.
So yeah, for your first comment there, we don't have what families are living in the T2, so the T2 is obviously going to be a specific type of family that are buying these types of apartments. But the most we would be able to do is control for neighborhood level, children level, so that's why we include controls for less than 19, older than 65, to try to capture demographic aspects of the neighborhoods. And yeah, it's on the list to look at how to control or measure accessibility differently. So we would want to explore travel time or road
some of the trees will have negative value. Why people not remove it?
Move.
They'll cut it down, whatever.
Well, these are publicly managed trees, so I think there's a process. Yeah, it's not up to the residents to decide which types of trees are being planted. These are being planted by the city.
Yeah, but I mean, people still have a moving power.
Yeah, of course.
They can,
So-
have their agreement, disagreement.
Yeah, so that would
I
be,
mean, I want to get this popularity issue.
Yeah.
We should both,
yeah, so if we would be able to look at, some panel data over time to see movements, then we might be able to explore that. But for now, we can't explore, what the solution to affect the people moving to different localities in the city. But it would be.
This is our common work with Raja Shakir. It is devoted on the study of climate-induced land use change in France. And we will try to look more on the impacts of agricultural adaptation and the climate change and mitigation policies that will be implemented in the future. So briefly, we are going to try to propose a methodology for the study of climate-induced land use change, and as I will show later, we know that climate change is influenced by land use change via the emission of greenhouse gases, but also it can work the other way around, as climate change is affecting agricultural yields and forestry yields, so we can have reverse effect on land use. And I will introduce first on the subject, then I will present you the model we use, the data, our estimates, and then I will present you some of our results in terms of climate change and public policy simulations. First of all, we know that for the last 150 years, land use change has been the source of about 35% of the greenhouse gas emissions from human activity. And it is also the principal vector of human impact on the environment, as it affects climate, it affects also ecosystems and hydrology. As I mentioned before, it can also be the result from climate change, and as we try to control this evolution, we would like to introduce some public policy that could limit the land use change, so we don't have the adverse effects of it. And in this paper, we will seek to develop a methodology for the simulation of this climate-induced land use change, and look also at the effects that we can predict at the 2100 horizon. So what we're going to look at are 4 general types of land use, which are agricultural, forests, urban, and a generic class other. What is specific in our study is that we're going to use data from mathematical programming models for two economic sectors of agriculture and forestry, which differs from most of other studies that are using actual data observed And we're going to combine these results from the sector-specific models with demographic information and land characteristics like soils and slope. And the main advantages of our methodology is that we can take into account some adaptation measures of the agricultural sector and of the forestry sector. And we can also simulate the effects of different public policy scenarios. We're going to see this later. This is the methodology. So we have our special econometric land use share model, which accounts for the competition between different languages, and it also accounts for spatial autocorrelation. We have the data from the two sector-specific models, which both have bio modules that simulate the future yields under climate change scenarios. And we have some information on the demography, on soils and the terrain, as I mentioned before. And here we have the two simulation scenarios where we combine also climate change scenarios with climate change mitigation measures. This is the specification of the model that we use. So we have our share of land use K in each grid cell, because we're going to work at a grid cell of 8 kilometers per 8 kilometers. And we have the expected share for our use and some error term. This expected share is defined in this specification. And we can linearize the model through the approximation proposed by Zellner and Lee. And as for the choice of spatial model specification, we've conducted a previous study where we compared different spatial specifications, and we've concluded that the same model is providing us with satisfactory results, and we stick to our point that we don't know exactly what the processes of spillovers is, so we're going to keep with our specification under the spatial error model, which autocorrelation may be due to the fact that we use artificial grid, and we have some omitted variables influencing the land use decisions by landowners. So this is the form we keep, and we use the metric that was obtained through linear triangulation of the centroids of our grid cells. The form for the predictor is provided here. We don't account for the effects between grid cells, as in the future we don't know what the error terms are going to be. These are our motivations why we use the same model, and we make our estimates with the error package SDF, and we use the matrix option to optimize the calculations. The data we use, we derive our land use from the Greenland Cover Survey for 2000. So we aggregate the different classes in 4 main types. The original scale is 1 hectare, and we aggregate them at the scale of 8 kilometers per 8 kilometers. The forestry revenues, as I mentioned, they are derived from the specific economic model for French forestry sector. And this is a partial equilibrium model, so we're going to be price takers at the international market, but we're going to have some price adjustments at the national market for forestry products. We also use the population density revenues to approximate the urban rent for the urban land use. And the agricultural rent is approximated by the gross margins derived from a supply-side agricultural model, which is originally available for whole Europe, but we stick to the results for France. The scale for the two models, Arropage and FTSM, it's the administrative region. So we'll have a lot of cells which have the same agricultural rent, and we're going to account for the heterogeneity of these cells by our variables concerning soils and the relief and the slope. So these are our results. We see that gross margin is significant and positive for agricultural land use. Forestry revenue is positive and significant for all of the models. Here we have agriculture compared to the other use. Here we have forestry compared to other, and urban. Population density has a negative impact both for agriculture and forestry, and a positive for urban. As for population revenues, we have both positive effect for all three models, and the most important impact for the urban. Slope has a negative impact for all of the models, as we expect that. If we're in the middle of a mountain and we have a great slope, we are most probably not going to have any economic activity from agriculture or forestry. And texture, it also has a positive impact for all of these activities. As we can see, our Morancy statistic is significant, and also our lambda coefficient for the special error model is also significant. We see that we have an increase, we have a better score from the INC comparing to the OLS model. These are our results. So here we have the actual land use shares. Here we have the results for the OLS model, and on the bottom row we have the shares predicted for the same model. So as for our climate change and policy simulations, we simulated two climate change scenarios, A2 and B1. These are two quite different scenarios, as the A2 is a rather pessimistic one and the B1 a rather optimistic. And in terms of public policy, we simulated two levels of tax on mineral nitrogen inputs, as the application of nitrogen by agriculture is one of the main sources for from agriculture. You have two greenhouse gas pollutions. You have either nitrous oxide or methane, and methane comes mainly from animal manure, and nitrous oxide comes from applying the nitrogen fertilizers on field. We have also two other types of pollution originating from fertilizers use. We also have nitrates that pollute oils, soils and water bodies. And we have ammonia emissions, which is a local pollutant and affects outdoor equipment. Here we have the simulations from the Arupage model. And we see that we have effects which are quite different from one region to another, as agriculture between these regions is quite different and is affected differently from the tax. We have regions which use more nitrogen fertilizers and others that use less. So there is a difference in the effects. We see that this is the case where we don't have climate change and we only apply our tax. We see that the two levels of tax, they lead to a decrease in agricultural land use, which is what we would expect, as applying the tax would reduce the revenues for agriculture and thus the agricultural rent. We have an increase for the forests. And what is specific for the Arupage model is that it accounts as well for crops and for animal breeding. So we have pastures, and in this column here we can see that by applying, initially we had like 25% of the agricultural area that was devoted to pastures, and if we apply our two tax levels, we increase the pastures area, as we do less crops. Uh, we see, so this is for the scenario where we don't have climate change. Here in this slide, I presented the results for the A2 climate change scenario. The simulations from the Aeropage model tell us that, in fact, agricultural revenues under climate change for France would increase. This is under a hypothesis where we can irrigate quite a lot, so they should be taken with some precaution. We see that this extension of the agricultural use is mostly at the cost for forest use. And when we apply the two levels of nitrogen taxation, we can restrain the increase in agricultural area. And this would be interesting in terms of also in terms of pastures, as once again our tax has an effect on pastures share. And for the B1 scenario, we have also a positive evolution for the agricultural land use, which once again is limited when we apply our tax. And we have a less extension for the urban use, because the A2 scenario supposes that there is going to be an increase in the demography for France at the 2020 horizon, while the B1 scenario predicts a slow decrease at the end of the century for the population of France. So this is what drives the results in terms of urban land use share. These are the predictions. We see that there is a greater extension of the agricultural use under the B1 scenario, and less forests also. So I would like to conclude here, and we see that as we use an artificial grid scale, we should take into account spatial correlation, and our results show that both climate change scenarios would lead to an increase in agricultural area at the expense of forest. A tax on nitrogen fertilizers can restrain this progression, and what we would like to do in future is also take into account the potential synergies that different environmental objectives can have, as nitrogen fertilizers have also effects on other environmental issues, not only greenhouse gas emissions but also water pollution. And also there are greenhouse gas emissions related to the land use change that we haven't yet accounted for in our study, and they could reduce all these synergies can reduce the economic cost of our mitigation policy, because I didn't comment on the figures, but nitrogen tax of about 50 or 100% per ton of nitrogen, it's leading to a really high abatement cost. So it should be argumented that there are other benefits than just the greenhouse gas emissions abatement. So thank you. Thank you.
So one of my main questions, the use of your spatial weight, do you use any different types of weight matrices? And because you use the grids, so I guess you're probably using a contiguous weight matrix, but whether or not you're using different forms to kind of check if the results are kind of robust against these. Then testing in the spatial dependence in the corrected model to see if you kind of corrected for the spatial dependence in the error. Then the use of the spatial grid, so whether the 8 kilometers can be kind of translated onto the communes, for example, and to see whether the grids versus the communes give you different results in the spatial, the model. And then if there's any kind of, I know the Paris 2020 climate change policy is a big kind of discussion going on, whether the model can be adapted to kind of calibrate to a very stringent 1.5 to 2 degrees Celsius and see what, what are the impacts of that. So those are the points.
Thank you. We first used the special weight matrix by triangulation,
Okay.
but now we're currently working with the integrating matrix. But I haven't had yet the time to apply this to our case study here. So I would really like to do this in the future. And thank you for the work with Morani.
Yeah.
I will look at this. As for the choice of the 100-year time span, in fact, our two models, the sector-specific models, our page, it's the agricultural model. We only have simulations for the end of the century, so we had to do this for this time. But currently there are developments on the model, so we will have short-term evaluations. As for the special unit used, in fact, we use this 8 kilometer per 8 kilometer grid because this is the grid at which we have some climate information, future climate scenarios, and we stick to this grid because we wanted in future to check our results comparing to other models that are going to be more using more likely this data at this case. As for the last note, and I think this evolution of temperatures it coincides with the B1 scenario.
Yeah, I wasn't sure if it was one of them was more likely
Yeah,
to that.
the B1 scenario it's more or less
Stringent.
something like this.
Yeah.
So thank you very much.
No, thank you.
Are there any comments?
Just one question to understand how you treat the share model. You have a share model by people can use.
Yes.
Okay. It's evaluated separately, or do you consider spatial effects between different types of use?
In fact, it's estimated, each equation is estimated independent. And then we have, because we know that all land use shares, they sum up to 1. This is the way we derive.
But no covariance between.
No. But yet we have all the variables for each rent of each use in each equation, so more or less this controls for.
There's a question about model. What is the channel you use for your the nitrogen effect on taxation on land use? And do you integrate the fact that the change in rotation, crop rotations
Yes.
towards the use of others more friendly,
Yes.
water friendly?
In fact, this is one of the advantages of using a sector-specific model, because in the sector-specific model there is a land allocation between crops and between cultures. This is from where we have the effect for pastures, because we know that if for a given field we can apply less nitrogen, so it would be less benefit. Maybe it's better to put it in pastures and have animal breeding on it. So this is one of the things, one of the adaptation measures that we account for, because not only in terms of taxation, but also in terms of climate change scenarios, we can account for crop switching. And we are currently, colleagues that are developing the model, they are currently working on the irrigation, taking into account water so that we can control and restrain the irrigation for our climate change scenarios. So it is still a work in progress, but results and the methodology is quite interesting because it allows us to account for a large number of adaptation measures. Is also for the trees, because in the forest model there is a managerial choice what At the moment, they cut trees, what trees they are going to replant. So they choose the tree that is going to be more profitable in future. So
Now, Elizabeth.
Yes. I think the only policy you have using your model is just the tax, correct?
yes, for now we only simulate this policy.
Right. My question is, we all know that zoning policies also affect land use change. So how do you think introducing, zoning policies would affect your results?
Zoning policy?
Right. So for instance, urban rooftop, which wouldn't prevent, which would prevent, converting agricultural land or forestry land into urban use, for example.
Yeah, we don't restrict the land use changes in this version. We only the policy we simulate. We account for its effects through the effect on profits for agriculture, and we would, if we were controlling for zoning, we should control, for instance, for natural reserves, for forests, because some forests are protected and they are not going to be converted, or at least not without any public decision that should be taken. But as we're at a really long-term horizon, we decided not to restrain the possible changes in order to study for the effect that the climate change can have if we don't take measures to it's like more to see the tendencies, not really to see what at one point would exactly happen, because it's really not quite possible to know what is going to happen in 2100. It's the models we use, we have like technologies that are from today. We know that we're going to have progress, and so it's really, we only wanted to see what the tendencies would be if everything is like possible. So thank you.
Okay, I'm from the stage, and we're lucky to have Professor Lamprey Lee to talk today about special methylated monols, time-varying endogenous weights, and common factors. For this session, so we'll take 15 minutes and save 10 minutes for questions. So about 15 minutes, and save some time for questions at the end.
Thank you. Absolutely. Thank you for inviting me to be here. This talk, in fact, follow up one presentation I have a couple of years ago. Jam was in charge of this workshop, and then we presented the panel data model and the time value W. At that time, the WT are all exogenous. And in fact, we discussed an issue for that conference. Jim found out, if the WT changes over time, it should be endogenous. It's not really that exogenous. So in fact, we follow up, on this problem. What he has criticized, and then here is one of the paper. In fact, I and some of the students we on this topic, in the series of papers. This one is is a panel data. The time, the WT is changing. Why it's changing? Because we're expecting, there are economic factors influence the network from the links, or the spatial network links. So if that economic variable influence the links, maybe also can influence the outcome. So then the outcome equation will become endogenous. So that's what we try to talk about. In factor models, however, there are different versions of how to control specific effects. In the classical literature, when we have panel data with long time, we have introduced individual specific effects. They are not changing over time. And also we introduce time effect, time factors we can observe, influence everybody. But in the same way, so this is an additive kind of model. However, there's literature now going on, and something like quite active, and that is to study common factors. And observe common factors, and common factor of individual districts respond to the economic factor and observe economic factor with different effects. Okay, it's not common factor influence everybody the same way. Some region may respond strongly, some region may not respond at all. So that's a coefficient in front of response to the factor. In fact, think about this as a coefficient. So that's called factor loading. And then, of course, once you allow factor loading, that means maybe different factor have different economic meaning. A different factor district respond differently. Right? So also, number of factors matters into this system. And also, one thing good about it is because if the factor loading is a constant across all the districts, that is the time factor is just one of the kind in the panel data. So so this factor model can be also as an extension of the additive panel data structure. So that's more rich because so that's in fact what people are interested about. And we want a panel data to have time factor in particular for spatial models, because spatial model usually we try to model the local interaction. The time factor is a strong kind of cross-section dependence. Something like Pessoa has keep on emphasizing on that, because everybody is being influenced by the policy, by the observed factor. So we need to distinguish the local factor and the strong factor. So if you just have a spatial model without controlling for time effect, you miss the strong correlation pathway. Okay? If you so that's why part is important to control for the time factor, and now this becomes a little bit more general. But however, this problem in fact create technical problem, because when you have this kind of product, right? What we have to say, look at this is just a panel data of an individual over time, and we have the W change over time, right? The regressors, but here the factor. So the FYT are the factors, influence the Y, but different regions respond differently. So you allow this is common factors. Well, there are different ways we can think about it. What we should do. In this case, we treat them as all unknown parameters. So the time factor and the individual response, basically individual effect, but then now with a multiplicative way. And this can be also finite dimension factors. The question is, when you estimate this model, you want to estimate not only the lambda beta, you have to also estimate those factor loading and the time factor. So you have many parameters problem. And of course, if we need to be able to estimate those factor loading and factor consistently, and that can be done only when we have a large N and T, unless you want to some method to eliminate this kind of factors, then you can think about different idea estimation. But if you want to estimate simultaneously the factors and unknown parameters, we have to look at the case, and N and T should be large. Okay, so that's some this line of that methodology. Okay, so this is a factor model. In the literature, we have several papers, and that is, for example, we have if the W exogenous, and we have time factor, and one paper I studied with my student, we talking about that. The question is, how to handle the estimation method. And we have this this product. What complication come in when we have W is endogenous? W endogenous, W may be, its element inside W may be a function of some other economic variable, Ci, Cj, and they change over time, and other factors, something like distance. So these economic factors, we just model it also, this can be multivariate. So this is a pendulum regression also with time and loading, a time factor. But this can be multivariate. Okay, so that gives some idea. We want to model the W in terms of economic variable, and it can change over time. So W has to change over time. But here, the other term, other term correlate with this outcome error. So that's the endogeneity come out. If it's not, then we just have the exogenous WK change over time. So here, this additional complication of correlation that's allow this W correlate with the Y. Because the W now correlate with the V and then correlate with the Y. So this is the endogeneity come from. So what we can do is to control for this endogeneity. That's my previous work with Sikri here. We have a cross-section data model, and also another paper with Yu and Xu. We're using additive factors. But here, this is a product, so that's technically become more complicated to deal with. Okay, so in terms of when we try to control endogeneity, what we have done is simply use one of the approach is to treat that as a control function. So we're conditional on the C variable is will become additive term. Something like if it's normally distributed, this is a conditional mean of the early term, outcome given the C variable. So we, basically endogeneity is saying, well, this parameter, this vector parameter is not zero. If it's zero, then we are exogenous. So this is a simple case of control. Of course, if you are interested in one-parametric, then maybe you say, oh, okay, this may be more complicated than a linear system. Theoretically, I can always generalize this to be a polynomial, finite order polynomial. But if you don't know the order polynomial, then you have to think about shift estimation, other things. In this paper, we just look at that as a linear kind of control function. So basically, given this control function, you can think about W now is exogenous because early term, after the conditional early term are correlated. Okay? So this is the way, simple way to treat that problem. But here, complication is because C in fact enters the W, so when we cannot really treat C as exogenous. So in here, because C appear in W, you have a nonlinear system. So when we nonlinear system, when we try to study the property estimator, we have to use a lot of large numbers, central limit theorem. And apparently, I think most design model we using the martingale property, and here it doesn't apply, cannot be applied. So what we're looking at is to some nonlinear econometric method for spatial kind of system. And apparently, then what we need to do is we are exploring what Porcher and Jennings and Porcher have developed, and that is NED, near epoch dependent. So in near epoch dependent, then we can talk about the raw large numbers, sometimes central limit theorem. Okay. So we have this kind of technology on hand. We can be able to handle some property of this model. There's a complicated part. But here, first we have to think about how can we estimate this parameter. And because now you have this complicated, product, right? Also in the C equation and Y equation, how we estimate. Apparently, it turned out to be interesting because that's well known somehow. That is, we can do that by using principal components. Okay. So what you do is try to say, for example, you know other parameters, right? And then we don't know the factor and the loading. What can you do? you can, just doing kind of concentrate, kind of likelihood idea. Given the factor loading, you can estimate the time factor by regression. And you look at the sum of square residual. And then, after that, then you have this objective function, and then you want to, this is a projector, orthogonal projector, something of this kind, and you want to take this matrix, this factor loading, such that you can minimize the maximum likelihood approach. So you minimize this residual, sum of square residual. And that problem exactly turned out to be a principal components problem. The solution is, depend on looking at the eigenvalues of those, this matrix. Okay, so you look at all the eigenvalues, and then you pick the solution is the sum of those smallest one. Okay, on those eigenvalues. And here then, that's the percentage likelihood. Now I can concentrate out the time factor and the factor loading, and such that will turn out to be what we don't know about is the structural parameter, lambda, beta, something like that. But unfortunately, this is a part of the structure. It doesn't have factors, but we have to. This does depend on the lambda and the beta. So when lambda and beta change, this matrix change, eigenvalue change. Okay? So this complicates the story because now non-linearity not only in the SAC transformation, but also enter into those eigenvalues. A question then, how to do that simple analysis? There are a couple of ways we can do. One approach is Bay approach, you directly look at first order derivative, something like that, before expansion. Another approach is more elegant. That is introduced Martin Wehner. He's now in UCL. He graduated from the University of Southern California. He has a paper with Moon in Econometrica. They look at linear panel data, linear regression panel data, the factor loading. And then using this method, question is, how do you expand this objective function in terms of the parameter data? So you can do, something like when you such as in property and nonlinear estimator, maximum likelihood, you do tailor expansion, or either from the likelihood function itself or from the first order derivatives, right? And from there you can do it. But here, how do you expand, expand this function in terms of parameters? Okay, because eigenvalue is not obvious. Can pick the derivatives. But fortunately, that's a literature. Numerical analysis, you have more application in computer science, and that is the perturbation theory. When you perturb, this is a matrix, you know about eigenvalue. Now you change the matrix a little bit, and what eigenvalue will, how the eigenvalue will change, okay? So you know original this eigenvalue is here, if you know that matrix, now I change the matrix bit, and what happened to the eigenvalue? Well, I mean, this problem, of course, very interesting for computer science because you're lumping error. So you want to study how the lumping error has effect on the computation of eigenvalue, right? But it turned out to be we can also explore in that theory to do expansion of that, this eigenvalues, okay? So that's what Martin has introduced. In fact, he has a PhD in physics. And physics people like that kind of style. So he's the first one to enter, introduce the perturbation theory in econometrics. And it turned out to be quite elegant theory. So that's what we also exploring. But we have a more complicated model because we have the SAC model. We have something like this kind of term. That turned out to be, if we can handle the expansion, this term can be handled somehow, and we can study the support theory. Okay, so basically, we are exploring this kind of expansion. But however, even you expand it, you have nonlinearity. So we have to look at this kind of, the LED, the linear process. we want to study the outcome, in fact, is the near epoch dependence, such that we can exploring what Jennings and Porcher have proposed, and such that we can apply the law of large numbers. Turn out the central limit theorem is a problem we cannot explore. But law of large numbers still useful, and this is something statistics involved. So when you have a near epoxy, you assume the units are located in Euclidean space. Now, of course, just the cross section, you have people located at different locations. But however, you have time, the time, you also assume the time process should be width dependence, and that's a near epoxy. Also, you can use near epoxy dependence idea. So what we have done is expanding space with time together, and so we can merge the space NED and the time NED into one big framework. So now you are living in, instead of say people live in 3-dimensional space, you pass time with 4 dimensions. So we are doing the same thing. Suppose originally you locate people in a 3-dimensional space, we have a time, we have d plus 1. Okay? So now you are living in a high dimension with time as a dimension. But you can moving around, so we are allowing some individual can connect with his parts. So each individual at different times is located in the space. So one individual at t time, we have t location. Okay? But depend on, we don't allow in this setup, because we are needing model how individuals are located in the space. We just assume that they are somehow located in the space in such a distance. So that's a very simple kind of setup. But using that technology, we can study asymptotic. Here, however, this literature only handle the increasing domain asymptotic. The individual cannot live very close to each other, at least 1 unit from each other. Okay? If you're very close, you are infer asymptotic, that's no literature yet in this field. So it's everybody has to live away, so you have district to district, right? Okay, so that's what we explore in this situation. In fact, why we need to explore, because we figure out in our research with C as a queen, and we recognize, this nonlinearity, in fact, can be handled without this theory, but however, become complicated to check how the law of large number can be applied. And you have to use Chebyshev inequality to find out, the high nonlinear function, what's the variance, and then the variance go to 0. It's too linear. And use this nonlinear theory, we can help you a lot. Okay? So we don't, so that simplifies our estimation. However, that's the price we have to pay. And that is, the W cannot be too general. Okay, so for example, when Paul talking about the distance, the W is a function of distance. We cannot allow that too much. We can allow, distance, but when the distance too far away, everybody cut off. Okay? So individuals with a certain distance, they can interact out of the distance, they cannot. So we allow spanners, basically, spanners, sparsity in the W matrix. That's a technical requirement. In application probably all right. But also, so here, that's our W. Where W will be depend on economic variables, CI and CJ, but also the distance control for the truncation. Okay, so you are smart W. That's the technical requirement basically. So we have a function. The W is a function you specify H function. In terms of CI, CJ. H also have some differentiability property, Shift condition, hold, something like that. To allow us to study the time dependence. Okay. Turn out to be also technical problem, because once we assume this W, in the space, then of course we can try to check the process, and then some of the statistics we can apply the law of large numbers from using the MED. But however, because we have fixed effect, when we estimate fixed effect, we're collecting, the data. Because something like individual effect, you want to estimate the individual effect, you take time average, derived from the time average. Okay? If you have time factor and you want to estimate time factor, you take a cross-section average and derive from cross-average statistic, derive from the cross-section mean at here. That destroys the NED property. Because you collapse the space, collapse the time. It turned out to be, we have to handle that problem. So it turned out to be, we have to really do something. And this paper, in fact, is a generalization of what we have done in the Quigley and Yu paper. There we have a simple projector because they're additive. They are only additive kind of effect. So we have a very simple derived from time mean, derived from cross-section mean operator. But for this factor model, then this will be replaced by this kind of projector involving factor loading, factor itself. However, in that theory, we can prove when we have this kind of quadratic form with this complicated g function. G is a function of w and inverse of I minus lambda w. So one linear function of the w. You have a projector. So the question is whether this we can apply more last number. So we have to really prove this one. And from this paper, in fact, we go through that, and this is easily generalized to this general projector. The reason is, even a general projector, it can be written as a sum of this form, okay? Something like this kind of, outer product, outer. Each outer product is very similar to that one. So it's just the averaging. Use this weight. So this can be easily do once we know, how to get the result for this special project. So this also helps us to handle the factor model. So basically, we have the thing we want to do. Okay, so now we know that we have what we have, and then we try to prove consistency. Now, usually consistency is hard to prove if you don't have the limit of the objective function. And that's the case, right? Here it's difficult, but turn out to be there's a general method. You can do that without looking at the limit, and that is by Wu's paper in nonlinear regression in 1981. What he has suggests is you want to prove consistency of the estimator. You look at basically this kind of excitation condition. That is, this objective function at true parameter is larger than other values of the objective function, especially when it's outside of the neighborhood. Okay? So outside neighborhood, you look at the maximization, the QN phase 0 is really the true one, and the probability of getting that is close to 1 when you like the n and t go to infinity. This is called excitation condition. I think this is also used in a lot of Peter Phillips using his study of the stationary time series, stationary linear time series. So this is very useful. And also, try when you're in the proof, the difficulty is how you need to find bounds, right? You want a lower bound such that this lower bound. So how do you get a lower bound? You first look at each Q, and you look at the lower bound. You find lower bound useful, and you want the upper bound. And the difference is this becomes lower bound, and the lower bound, we need to have some identification condition such that we can establish strictly inequality with probability 1. So that's a little bit tricky. But one thing good about this approach is you can easily figure out the initial rate of convergence. It's not a very good rate, but in this proof, we get consistent, also we get a numeric rate of convergence. Of course, we need some condition here. A little bit complicated, basically, is the regressionist matrix, and then put it for each variable is n. You put an NT matrix, and there are some variation. You cannot have time invariance or invariant time variable. This environment is sufficient condition. The reason is if you have time invariant, individual invariant variable, they absorbed by those factors. Okay, so that's important to identify. So what you have, the regression has to change over time and change across individuals. Okay. Of course, also we might become linearity across the variable, right? Something like that. Basically, that's the condition we need. Right? Also, in space, we can explore the correlations of the reduced form of the residual. Right? So that, of course, you have to assume the residuals are no spatial dependent, all right, no time dependent, so just independent. Or sometimes ID, but you can exploring, this kind of reduced form, covariant structure, and explore to get the lambda. Okay? So that part 2, right? The previous part is something like we can do estimation with IV. Okay? So in this case, when there's a big condition, we get identification, and but here the question, that's an interesting problem, because in factor, how many factor matters in estimation? You don't want to specify the number of factors less than the true one, okay? Because then you're missing an important factor. You have to specify many more factors, okay? So if you can specify factor at least larger than the number of true factors, then you're okay. Okay. So in general, that means you have to be, generous to allow more factors in the estimation. Okay. For consistent, that's no problem, not a big problem. For asymptotic distribution, however, that's the difficult problem. Okay. So here, if you can do that, if you really specify enough factors, can be more than what you want, the number of factors, right? Because we don't know it. Right? But you can prove this is consistent, and with a certain rate, the rate is just the minimum, square root of minimum NT. Okay? So it's not NT square root, it's a minimum. So it's the rate is not that good. But you look at some rate in this proof, right? When you use the excitation condition. So that's the nice thing about it. Okay, now asymptotic normality, then it's really, right? That's the hard part. And then you use the perturbation theory to do that. Because you want to expand that, according to a Taylor expansion. So the idea is you look at this matrix and you want to expand it in terms of the parameters. So the parameter in terms of beta, lambda, something like that. Also the variant matrix are no parameter. But this theory is a linear algebra, linear operator theory. So you need to have this, say this inverse of the variant matrix. You need to parameterize in terms of linear function or unknown parameter. Well, that can be done just depending on how you define the omega. That's the matrix. But anyway, you linearize that such that in terms of unknown parameter. Okay. Then this matrix in terms of unknown parameter is a polynomial. Okay, so you can write down, this as a function of this unknown parameter, derived from unknown parameter, and those are the perturbation term, because those are small terms. So you can easily figure out what's the value, the eigenvalue for these things, but this is a little else you have to put in, and you need to expand that term, okay, for this eigenvalue. Okay, so that's the perturbation theory coming into play. Eventually, we know that, and of course, we have to also assume the factors. The true factors are strong. Okay, in the sense, if you look at the matrix, we say the loading, the product divided sample size, limit has a core definite matrix. So the factors, in fact, are there, and they're useful. Okay, they're really playing a role. Okay, not zero, something like that. Okay. Now, in that case, we need, because this assumption, we don't need to know exactly the number of factors to get asymptotic theory. We cannot say you are more, we can be more generous than put more variable, more factors than what you need. So the asymptotic normality become more restricted to find it. Then in that case, you can expand, the long linear function in terms of the true parameter, in terms of this kind of quadratic form. That's exactly the way you get asymptotic theory by Taylor expansion, right? Okay. You see, this is the asymptotic normality comes from these two terms, when the Hessian and the score, basically. Okay. But that's not just a Taylor expansion that easy. So that one is interesting, quite elegant, because you have general theory for perturbations. Okay. And I think in this approach also very useful to look at high orders of properties. Because you can also look at other terms. Right? We just pick up the the simple terms, for the first two terms, we find the high order terms here, small term. If you want to study high order asymptotic, this term will come into play. And you know the formula. Okay? So that is one. But anyway, this will turn out to be. So once we get this one, then probably we can figure out what's the asymptotic distribution. This is the Hessian matrix inverse. This is the score. More or less, this is the score vector. So asymptotic normality apparently will depend on this score vector. And interesting to figure out, yes, the score vector, in fact, is a linear quadratic form. Well, that apparently bring about, whether we can, what's the complication is, we have two kind of errors. One error is the error in the y equation. Now that is after the control for the endogeneity, we have, that side. That is the error term in the outcome equation after condition on the C. But then the C variable also have error term. So there are two set error term, epsilon and the psi. And this is a linear term for the epsilon, a linear term for the psi, and quadratic form for the epsilon, quadratic for the psi, and a cross product. Okay, so this is a quadratic form for two sets of random variables. They are correlated. But this is not that complicated. I mean, we can generalize what the quadratic central limit theorem to the two error case. That's not a difficult problem. The difficult problem is this kind of weighting matrix of the linear coefficients may be a function of the error term. But lucky enough, when this outcome equation, look at the outcome equation, this B and this B and this capital B, right? And also, this this guy also, I think, this guy doesn't matter. This B and B is a nonlinear function of only epsilon, not psi itself. Okay, this A and this D are constants. So you have nonlinearity in the quadratic form, but it's a recursive. In the recursive one, right? So if you look at martingale, it still works. Because the psi can condition on an epsilon. Okay? So that's still a martingale. Even it looks like it's not completely quadratic form for the two variables. But it is when you condition the psi condition on epsilon. Epsilon, that is a quadratic martingale. So that turned out to be a generalization of this martingale central limit theorem, and we can apply, we can find the central limit theorem using this function. So that's the interesting part, because we cannot use the central limit theorem to near epoch dependence. We have a projector to destroy much of the problem. So also here it turned out to be, when we look at the score, we have a bias term. And this bias term is because of the too many factors. You estimate, because the number of parameter, loading, and time factor too many, you create a bias. The bias has what an effect in the variance estimator. Right? But in the other estimator, the bias, the beta, lambda also has bias, but small order, beta has not. Okay? It is the variance that have some kind of bias. And that's so I didn't like the formula, but if you look at it, it's true. Okay? So, but this the bias we need to collect. It's the order of 1 over square NT. So we have the non-centrality of the asymptotic distribution. Estimator square root NT convergence, they have the non-centrality parameter, so we need to remove that. Okay, by subtracting it. By initial estimate subtracted and do the job. So if you do that, after bias collection, if it's not normal, you have this formula. If it's normal, just sandwich form becomes just a usual form. This is one effect. So this gives us the asymptotic distribution. Okay, so here now we want to see a little bit. Also, we have literature have some story on how to use a criterion function to select the number of factors. Okay? So there are several criteria in literature. We look at them. One is the AHAN, is an early one, 2013. It turned out to be useful. So, but it's a little complicated per se, so but in practice we do use it. So here is first we set this some Monte Carlo, and in this case, we have allowed two factors, and we also allow the x correlate with this factor. That's why interesting to assume the loading and the time factor to be fixed, because this x can be related to that, and you have the correlation, right? When you have correlation of individual effect with regression, the way you can handle this problem is to use the fixed effect instead of random effect. Okay? Random effect cannot do the job. It's complicated. So here we've done Monte Carlo. We assume the x effect also generated by this factor and some other additive factor as per the curve. So there's some correlation among that. And in terms of the W is simple. We just keep our board, 5 by 5, 7 by 7 individuals, and just use the near neighbor. Okay, but we assume there's a in addition to the distance, the nearby neighbor, the root structure basically, and then we have another, there's an economic factor, economic distance. This kind of homophilic basically, homophilic kind of factor, and they're very close. When the two the C, I and CJ very close, and the link is large. Right? And far away, the link is weak. Okay, so this is homophilic in the network literature. Okay? And then we also low normalize. Okay, also we control for the correlation. Some can be strong depending on what's the role we can talk about. That's a variance we control to look at the R squared, which are the factors more important than the noise more important in general. Anyway, this is the Monte Carlo result. Right, so here, okay, I didn't present, I don't have time to present the whole thing, so I just put down this estimate. But also we have a select number of factors. And turned out to be, the selection turned out to be useful in most cases. We figure out the true number of factors. Okay? So here, given you this, what we select the factors, and we see whether this is estimated bias not used. So this true parameter, is beta is 1 for the C variable. This for the Y variable equation. Lambda is 0.2. This is the 1 over the standard deviation of the Y equation. The alpha is 1 over the standard deviation in the C equation. This is the heterogeneity, coefficient, right? So it looks like in terms of, say 25n is 5 by 5 matrix, 5 by 5 chessboard, so 5 people. And 25 period, anyway, adding 25, 25, looks like the bias, rather small, okay? It's not that big. This is bigger, this one is, because the 2 is 0.87, this also, 0.3, right? So this one is the 10%, right, this one. But the worst thing is when we do the confidence probability, because these are biased, you have a very bad confidence probability. Instead of 0.95, now it's only 0.6, something like that, consistent. When you have a large sample size and T. So these are the bad things in particular testing because there's some substantial bias. But once you do correct bias, nice, it looks like close to the 95% coverage. So it looks like here is that this guy, and the other lambda have a little bit bias too, but the beta have not, and also this popularity does not. So the bias is really on the variance, a little bit on the lambda. And once you collect for it, you see the result pretty nice. So bias collection is important in this literature. Okay, we also get some strong, instead of just wick, we also put some strong interaction. So now I think we have landed 0.6 instead of 0.2, right? Landed should be between 0 and -1 and 1, right? So 0.6 is less strong. And also the anticonductivity also becomes stronger because we control some out noise ratio accordingly. So here we also get the same problem. You see the bias also can be can be some substantial compared to other one, but instead of first digit, second digit, right? First digit. And coverage probability also not under coverage. But when you do bias collection, it looks okay. So bias collection, in fact, can work for both strong or weak case. Okay, here, okay, that's the one we got. Okay, one thing interesting is what happens if you just hit the W exogenous? Is that important, right? So we expect what to expect. Well, depend on how serious is the endotonicity. If the endotonicity is stronger, probably you get more bias. Yes. Okay. So in fact, that's the sort of case here. For example, when we look at the beta is bigger. Is that what? We specify. Yeah, we have lambda 0.2 there. This lambda 0.6, and also the rho capture the correlation or other term, right? So one is 0.2, then 0.6, and then you see when compare with the 0.2 and 0.6, the bias is more severe. So of course you expect that case. One thing interesting to see is in terms of the endotonicity, in terms of spatial correlation, the larger or the smaller of the correlation, the spatial lag curve. If the effect smaller, the bias is less severe. Okay? No, the bias is more severe. The lambda W, if the lambda is small, the bias is more severe. Probably because this term is not that important. But once you have lambda big, then the bias is less important. Because the endotonicity is less important. Maybe because the lambda W is an important term compared with the additive term of the endotonicity. Okay, so that will be, in fact, that turned out to be general case also with sequence using additive. So this seems to be persistent. But you just have bias problem, right? So for example, the lambda is here, 0.6, 0.004, right? Something like that. And here you see even 40%, 0.2, 0.08, you have 40% bias. Okay? This guy, right? So there's a bias is there. Okay, so we are iterating this one with application and in housing data. So what we studied is to study the this mortgage, home equity conversion mortgage. Basically, this is for senior citizens in the U.S. You have your home, you want money, right? What can you do is you reverse mortgage. Right? You get money from the insurance company, they pay you, each month, but the house is, they're controlling your house, they can sell your house, right? So basically, use that house to get as a cash cow, okay? Of course, then the insurance company worry about you get the money and you don't take care about the house at all. The house become really bad sick. So government had to come in. Government support this insurance. When the housing price becomes so low, the insurer can always get the money back, no matter what. Okay, so they encourage the private company to give out the loan. So this become more popular nowadays because senior people have the asset. They want to use the asset to get the money, right? Okay, so that's what we try to do. And what interesting turned out to be is, there's, in fact, we allow 2 W. 1 W just economic distance, the neighborhood, right? Another factor is the W2 because in this industry, there are a handful of large insurers. They occupy about 40% of the market. So those big insurers, they can operate in several different regions, in particular certain nearby regions. So we think, this share of the big factors will, if they are really big for the two regions, then two regions are more connected because you're handled by the similar insurer. Okay, so that's introduce the factor into explain the W. In the second, in ethics economics, you have this big insurance connection. Other variable is look at the valuation of the housing price, derived from several years. You look at deviation of this period price to the previous average, and also look at the variance. So the idea is, a lot of variance in the house, and also price delay from the mean. Those uncertainty will encourage people to use this law to protect themselves. If you look at your price go down, you worry in the future, that's useless. You want to make sure you can get the money now, and so that variance is important. It's a nonlinear specification. Okay? So basically, we allow factors in here. Also that one. It turned out to be, in practice, we get one factor. And we can also estimate the factor loading. If we plot it, that's a lot of variation. Right? So it's not additive. Right? It's one factor loading that change for different states, and one-time factor. We don't know what that means. That's the problem. It's a factor. What's this factor come from? What that means? It's an observed factor. Right? That's the weakness in the factor model. So anyway, that's what we have. So this is the result, and basically, we see this lender, also lender 1, lender 2 are significant, and we see that continuity also significant come out here. Okay, and this is negative, but that's a cross-product term. So basically, when you look at that together, you do see the price variation and the price deviation have positive effect on people getting the insurance. So people protecting themselves. And continuity come out in this case. Okay.
Questions, comments?
Really a comment. This is fantastic. Thank you very much. For me, it starts clarifying the issue of factors, and in this large, together with the endogenous weights matrices, and that this interaction is very important. Now, I got confused somewhere along the line, and conceptually, I want to just get a couple of things clear. Okay. So, in a large N, large T setting, Pesaran common correlated effects work. Okay, so a maximum of k plus 1 factors is fine. We know how to capture them. K is finite, so that is not a problem. Right? The problem arises in situations when n is small or t is small. In that case, we can go for, under Gaussian assumption, we can do Jushan-Bai and stuff like that. Or we can do something else somehow to capture the factor structure. So really this is a small sample or finite sample problem. Alright? So if it is a finite sample problem, then the real test for this is not a large sample thing, it is some sort of finite sample asymptotics is what we want to look at, right? So either restricting n to be finite or restricting t to be finite and letting the other one go to infinity and try and see. Is that intuitively a correct way of thinking about it?
Yeah, because we emphasize on you want to estimate the factors,
right,
and the loading. Yeah. So basically, you want to sample individual fact, time effect. You want to both estimate consistently, and you need, for time factor, you need a large cross section, right? That's definitely. For individual fact, you need a long time series in order to estimate it.
Yeah.
We can avoid this problem if you eliminate those factors, eliminate facts, and then to do estimation. So that would be another one to start with in terms of estimation. Personally, I have idea, I think interesting using this method, but then you have to assume X have the, this X variable also have the factor structure. Right? So I mean, that increasing this factor structure. That one we don't assume. We just assume X is correlated in very general form. So that one, but I think you're right. If you want to look at short t, right? Probably we have to think about how to eliminate those factors, and there's some procedure available. Smith. I think they have idea how to get out that factor.
Basically, you have to use the Gaussian assumption and estimate the factors, right? So.
I think they eliminate.
Or eliminate.
Eliminate. Then we don't need to. I mean, if I factor the Gaussian, I have to think about is that a time series time factor, dynamic factor or not, and if the factor loading is that factor loading spatial correlated or not. I mean, you have to think about structure to do it. Right? Your random coefficient structure. Here we just very general. So either we estimate or get the effect. So far we are estimating. So we are last here n. But if you want to go for finite and t, some part of it, probably we can eliminate to see how to do estimation. Right? Or you have imposing structure, dynamic factor structure, or factor loading, ID, spatial correlated. Yeah, I think we can do something. This, I think, I still learn it because the first time I heard about the factor loading was in Cambridge. When I saw the stuff, I said, oh, that's fantastic. Let me think about it. But once you know the technology is not that simple. That's a lot of issues. Yeah. I think that's something. But I like the perturbation field because now if we want to study finite sample, I think it's possible. But you have to look at high orders of particle. Right? If the finite sample is 100% of our, that can be the case, especially Young have done. When you have a very dense W, I mean the things the fires can come out, so that high orders of particle is a way to handle it. But I mean, interesting. And more interesting, what's the meaning of the factors? Right? I mean, when they do the job, you just put in the independent data. The factor is something we don't know about, and just hang on as a background. We control for it. But I mean, when you look at the original macroeconomics or psychology literature, there are many variables, and you want to summarize the variable in terms of some special terms, like index. And you provide index, index to explain the factors. And here we don't have that. I mean, it's not that exactly because you don't know what the factor is. Factor R, So I think I'm interested in that. If you're macroeconomics, try to accept multi-value variable to explain that. That'd be interesting too.
Any other thoughts?
Yeah, this presentation idea is really fantastic. I mean, for this kind of model, such a complicated estimating of iron part metric is always an issue. Yeah, I'm wondering what kind of reasons you need behind this perturbation theory. Do you require to use symptomatic errors, for example, to be Gaussian to be normal?
No, you have to the Gaussian effect is why I have classification. When I do contact form, so that's not Gaussian. Right? I think if a statistic makes people out of the statistic, you cannot avoid that. But I think numeric is not an issue. So basically, you see I have 3 terms. So if normal, you can simplify that. Numeric is not the issue. The perturbation theory is very elegant because you can think of high orders and particle, and a lot of other things, you cannot do Hale expansion. And you can concept it out. Very concept right? You're working on instead of looking at whole set first order condition, and then try to do something. So this is elegant. And then also not just the eigenvalues, the main issue here, but other things we can do in interpretation. Right? So I think that's something interesting. And And so far, I mean, this guy will introduce this. I think that's something interesting, but in the future, topic more interesting thing.
Yeah, the perturbation theory is statistics long ago.
Yeah,
I
yeah,
never,
yeah.
I never really seriously think about using. This is a fantastic learning.
Yeah, it's a little bit hard when I look at it, even the perturbation field. My student can do a good job. And I look at it and say you have to know complex analysis. And you have to know, there's a lot of theory. Jordan canonical form, the linear algebra, all these things come into play. And you have this integral analytical function. So you find it, kind of number in the circle, you have to, this kind of thing. I mean, it has to be interesting. You have to know a little bit more complex analysis and analytical function idea to understand what's going on.
Another question I'd like to ask you, Glenn. This some sort of bias, I understand it all comes from the concentration, the concentrated out factors and concentrated out loading and the move magnetic degrees of freedom. So that's why you come up with this some sort of bias. But the question is, can you simply do it on the concentrated scores?
To revise that?
Yeah.
Yeah, I think here, it's possible, but I think so. That's something I use there. But here, I think we do the second step. After you get estimator and then you collect, you can use estimate. I think what you are doing, you have to figure out what's the bias term, and then directly solve the first order condition. So the first order condition is not obvious, because it's not really get first order condition. We are looking at expansion, so we have some of high order terms drop out. So if you look at the expansion only up to the first separate order, and then take the derivative, maybe then you can do something. The remainder term has to be gone and disappear. Then the remainder term, when you take derivative, have big gain effect. You have to be careful about that. It's not directly you can take a derivative. Unless you use base case, take derivative without eliminating. It's not directly from the concept of value. It's possible, but I'm not sure whether the first couple of terms will catch what you want.
Thank you very much. Thank you.
Okay, I think we're ready for lunch, huh?
So thanks for